In October 2025, a single press bulletin from a Japanese lab triggered the endgame for fossil fuels. It wasn't a discovery, it was a confirmation. A team of scientists had tamed a star on Earth, holding a plasma cloud at 120 million degrees Celsius for minutes, not milliseconds. Within hours, energy markets convulsed and the world's most powerful industry panicked. This is the story of the breakthrough that just changed everything. Let's delve into it. Breaking point. What if we could bottle a star on Earth? In October 2025, Japan's National Institute for Fusion Science, or NIFS, announced a historic milestone at its Large Helical Device. Scientists there sustained a plasma at an astonishing 120 million degrees Celsius for several minutes, a duration that is an eternity in the world of fusion physics. To put that in perspective, the sun's core is a mere 15 million degrees. Led by Professor Masayuki Yokoyama, a leading authority on stellarator plasma physics, the NIFS team used a sophisticated system of AI-driven magnetic fields and advanced superconducting coils to achieve this record stability. This wasn't just a lab curiosity, it was hailed by energy analysts as the closest humanity has come to practical fusion energy. The news released from Tokyo spread like wildfire across global news wires, instantly shifting the conversation around fusion from a distant scientific dream to an immediate and disruptive technological force. For the first time, the promise of clean, limitless energy felt tangible, forcing the world to ask a critical question. Did Japan just ignite the beginning of the end for fossil fuels? This achievement demonstrated a level of control that many thought was still decades away. Market panic. The news didn't just hit science desks, it slammed into trading floors like a shockwave. Before lunchtime in Tokyo, the reaction was visceral and immediate. Helical Fusion, a key technology partner for NIFS, saw its stock soar an incredible 23% by the afternoon, close, as investors scrambled for a piece of the new energy future. In stark contrast, shares in legacy utility giants like JERA and Tokyo Electric Power plunged 3% each as investors began to model a future where fossil fuel assets were suddenly obsolete. The Nikkei Energy Index dipped sharply as traders, guided by instant alerts, tried to price in this paradigm shift. The panic was not just in equities. Yields on major utility bonds saw a 7 basis point jump, a clear sign of rising risk and eroding confidence in their long-term business models. Trading volumes in clean energy ETFs spiked 46% in a single day as capital fled from the old and rushed toward the new. As confirmed by energy strategist Kenji Tanaka, the event triggered what the industry had both feared and hoped for, a genuine inflection point that made the promise of fusion a measurable financial risk for the old guard. Inside the control room, how do you control a substance 7 times hotter than the sun's core? The answer lies in a groundbreaking fusion of human expertise and artificial intelligence. Inside the control room of the Large Helical Device, engineers and physicists, including Professor Yasuhiko Takeri, the Director General of NIFS, monitored a digital twin of the plasma. This advanced AI model, running on supercomputers, processed trillions of data points from thousands of sensors every second. It predicted and neutralized instabilities in milliseconds, a feat impossible for human operators alone. The plasma, a turbulent cloud of charged hydrogen, was held steady not by brute force, but by precise, intelligent adjustments to the magnetic fields. The LHD's massive superconducting coils, cooled to near absolute zero, generated the immense magnetic forces required for confinement. But the real breakthrough was the AI control system that acted as the plasma's shepherd. A system refined over years by diagnostic experts like Professor Kenji Tanaka. When sensors detected a potential collapse, the AI responded instantly, tweaking power inputs and adjusting the magnetic cage. This record-setting run proved that fusion plasma could be managed in real time, transforming it from a wild, untamable force into a controlled and predictable power source. The magnetic bottle. To understand this breakthrough, you have to understand the bottle. You cannot hold 120 million degree plasma with any physical material, it would instantly vaporize. The container must be made of immense invisible magnetic fields. The Large Helical Device uses a unique design for this bottle, known as a stellarator. Conceived in principle by the brilliant American physicist Lyman Spitzer, a stellarator uses a complex series of external coils wound into a double helix. This creates a twisting, Mobius, strip-like magnetic field that guides the plasma on a stable path without needing the massive internal current required by the more common tokamak design. This inherent stability is what makes the Stellarator ideal for long, continuous operation, the ultimate goal for a power plant. The LHD's coils, massive superconducting structures cooled to near absolute zero, have been operating since the late 1990s. The hardware isn't new. The breakthrough, as the current NIFS Director General Professor Hiroshi Yamada has long envisioned, was always going to come from mastering the control system by pairing the LHD's proven, stable design with a predictive AI. The team at NIFS created a magnetic bottle that could finally hold its star indefinitely.
For decades of progress.
This breakthrough didn't happen overnight. Japan's journey into fusion research has been a marathon, not a sprint, fueled by the national imperative for energy independence following the oil shocks of the 1970s. The story begins with early organizational efforts by scientists like the Nobel laureate Hideki Yukawa. A key milestone came in 1985 with the powering up of the JT-60, a large tokamak reactor in Ibaraki Prefecture. For years, researchers at the Japan Atomic Energy Research Institute, under the guidance of physicists like Dr. Masahiro Wakatani, used this machine to push the boundaries of plasma temperature and confinement. In the late 1990s, Japan diversified its approach with the construction of the Large Helical Device. This dual-track strategy of developing both tokamak and Stellarator technology proved to be a masterstroke. Collaboration has also been central to Japan's success. The upgraded JT-60SA, which achieved its first plasma in October 2023, is a joint project between Japan and the European Union, serving as a critical support satellite for the massive ITER project in France. This long history of steady investment, global partnership, and relentless scientific inquiry laid the essential groundwork for the recent historic achievement.
Fusion fundamentals.
The science behind this breakthrough is both simple and profound. Nuclear fusion is the engine of the universe, the same reaction that powers the sun. It begins by taking two light atoms, usually isotopes of hydrogen called deuterium and tritium, and forcing them to merge. To do this on Earth, you must heat the fuel to over 100 million degrees Celsius, far hotter than the sun's core. At these temperatures, the fuel becomes a plasma, an electrically charged cloud of ions and electrons. As NIFS physicist Akio Sagara explains, the challenge is threefold. First, achieve the temperature. Second, confine the unstable plasma long enough for fusion to occur. Third, capture the energy released. The LHD's success was in mastering that second challenge on a game-changing scale. By holding the plasma stable for minutes, they proved that a controlled net-positive fusion reaction is no longer just theoretical. Unlike nuclear fission, fusion produces almost no long-lived radioactive waste, and a meltdown is physically impossible. If control is lost, the reaction simply stops, making it inherently safe. This is the promise of clean, safe, virtually limitless energy.
Financial shockwaves.
The ripple effects of the LHD announcement extended far beyond the scientific community, reshaping financial markets in real time. The theoretical risk of fusion disruption suddenly became a tangible threat to the existing energy infrastructure. Utility companies, heavily invested in fossil fuels, saw their credit default swap rates tick up, which was a clear sign of growing investor anxiety about their long-term viability. Lobbying firms representing the oil and gas industries ramped up their activities, filing petitions that cited the potential for core industry displacement. Meanwhile, the private sector's confidence in fusion really surged. The Japan Fusion Energy Council, or J-Fusion, reported a massive increase in private investment into fusion startups. Companies like Kyoto Fusioneering, led by physicist Taka Nagao, which focus on the practical engineering challenges of building a power plant, like heat exchangers and tritium breeding blankets, saw their valuations skyrocket. Venture capital firms, recognizing the immense potential, began pouring capital not just into reactor development, but into the entire fusion supply chain. The financial landscape was being redrawn, with capital flowing away from the past and toward a fusion-powered future.
Leading the charge.
At the center of this new energy paradigm stands Professor Masayuki Yokoyama and his team at the National Institute for Fusion Science. His name now appears on the papers that are redefining the world's energy roadmap. For years, Yokoyama and his colleagues have published research arguing that the LHD's stellarator design, when paired with intelligent adaptive control, was the most direct path to a commercial fusion power plant. Their October 2025 achievement was the ultimate validation of that belief, a culmination of a career dedicated to mastering helical plasma physics. According to Yokoyama's statements, the experimental evidence now proves that plasma stability can be maintained well beyond classical limits, with AI acting as the indispensable pilot. This success has galvanized Japan's entire fusion ecosystem and positioned his AI-driven control system as the potential global standard. The Japan Fusion Energy Industry Council, J-Fusion, immediately began coordinating with private industry to map out a supply chain for the coming demonstration reactors. The breakthrough wasn't just a scientific victory, it established Japan as the undisputed leader of the charge.
Government response.
How does a government prepare for a technological revolution? Japan's answer is with a deliberate and forward-thinking national strategy. In April 2023, the government unveiled its Fusion Energy Innovation Strategy, a comprehensive plan to accelerate the commercialization of fusion. This was a clear signal that fusion was moving from pure research into the domain of national industrial policy. The strategy aims to foster collaboration between the public and private sectors, with the goal of having a demonstration fusion power plant operational by the 2030s. This proactive approach, championed by officials like Minister of State for Science and Technology Policy Sanai Takaichi, contrasts sharply with the stances of other nations. Following the LHD breakthrough, METI convened a special working group to assess the disruptive risk of fusion and develop frameworks for a stable energy transition. This includes plans for creating robust supply chains for critical components and fostering a new generation of fusion scientists and engineers, ensuring the nation has the talent to see this vision through. Japan is not just reacting to the future of energy, it is actively building it.
The path forward.
The October 2025 breakthrough answered the biggest question in fusion science: can a star be tamed and controlled? Now, the path forward is about engineering, material science, and industrial scale-up. The immediate next step for the team at NIFS is to replicate the 7-minute run and push the duration even longer, aiming for true steady-state operation. This will generate the terabytes of data needed to design a commercial-grade reactor. This data will be shared with their partners at the JT60SA Tokamak project, where leaders like Sam Davis will integrate the AI control insights to advance that design as well, leveraging Japan's dual-track expertise. The government and J-Fusion are now laser-focused on building DEMO, a demonstration power plant that will be the first to connect a fusion reactor to the electric grid. The biggest challenge is no longer the core physics, it's about building the international agreements and regulatory frameworks to license this new technology globally. Japan's AI-driven helical confinement system is now the world's most valuable energy patent, and the race to build the first fusion-powered city has officially begun. Japan's fusion breakthrough is more than just a scientific achievement, it's a pivotal moment in human history. The prospect of a world powered by clean, abundant energy is no longer a distant dream, but a tangible goal that is accelerating toward us. The journey is far from over, but the path forward is clearer than ever before, and the implications are staggering. What do you think this means for the future of energy and society? Let us know in the comments below. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the technologies shaping our world. Thanks for watching Stellar Tech.